brain-computer interfaces are systems using the brain activity of people or animals and using this activity to activate external machines, devices, computers. So they take the brain activity without the motor activity, without touching the motor activity. So even people and animals who have no movement capacity anymore, they still have an active brain, and the activity, electrical or metabolic or blood flow activity of these brain areas is used for running a computer, a wheelchair, or any other external device. So the fundamental principle is using brain activity without the activity of the motor system and using it directly to communicate with an external device or with another person. That's the basic principle of brain-computer interfaces. Now, there are two big types of brain-computer interfaces. One, which we call invasive brain-computer interfaces, where we use the activity of the brain directly, which means that we have to go inside the brain and inside the head, and that means a surgical procedure, and then we stick our electrodes into the brain or in single cells of the brain. And then we use the activity of these single cells to run an external computer. Usually that's done in any animal experiments, but there are also some first human applications of this invasive procedure. You can also open up the head and put the electrodes on the surface of the brain without touching the brain itself or without injuring the brain. This is called electrocorticography, which gives you a signal which is much better than what you record on the top of the head. These are the invasives. For the non-invasive, which means you are not going inside the brain, you can use the standard electroencephalography. So these are the electrical activities of the whole brain, of millions of cells, and you record them by attaching electrodes on the scalp. This is the most frequently used activity for brain-computer interfaces. Second one is you can use, of course, magnetic recordings. That's more expensive, but more precise. So I can record the magnetic fields of the brain outside of the head. Again, there are some applications of this available, but it needs a magnetoencephalographic device, which is very expensive. Thirdly, also expensive, but very useful, are devices which measure the blood flow or metabolic changes of the brain, like oxygen content of the blood in the brain. Anytime you think, when you think something, when you feel something, the oxygen which is necessary for this thinking is brought to the cells after you thought it. And the more you think and the more intensive your feeling is, the more blood flow is necessary to run that thinking process. The method to record this, the most used methodology for this, is called functional magnetic resonance imaging, fMRI. This again is very useful, and you can look in the depths of the brain, in deep parts of the brain, mainly in subcortical parts where emotions or motivations are generated. So it's very useful for brain-computer interfaces which want to change people with emotional disorders. Now, in the last few years, another metabolic instrument, non-invasive instrument, is used for brain-computer interface, and that's called near-infrared spectroscopy. And near-infrared spectroscopy is very easy to apply. It's relatively cheap. You can have it portable. You just put light on the top of the head, laser light or other types of light, infrared light. The light passes through the brain, through the scalp, passes through the bone, touches the brain, and the more blood flow you have in a particular part of the brain, the less reflection you get from the light, and that you can measure. So that with this trick, you can measure the ongoing blood flow and the ongoing oxygen consumption of a particular brain area. That will be very useful in the future, and the first experiments are very positive.